synchrotron afterglow is fairly well verified. The other nice surprise that was detected in 1999 was that there was a prompt optical flash. And this was achieved with very small little telescopes. Look at these. These are Nikon cameras, telephoto cameras. So a set of 4 telephoto cameras, but they're mounted on a robotic mount that can, when you get, so the Pepple-Sachs satellite sends down via internet within 10 seconds an alert that there is something interesting occurring in these regions. So these cameras could repoint within 10 seconds and look at whether it sees something. And it's the first time that it detected something within 10 seconds or so after the alert. And it was a very bright optical flash, 9 optical magnitude. 9 optical magnitude is a very, very bright, comparatively bright object. And it was initially a fast decay and then a slower decay. So in fact, this slow decay is what was expected from the reverse optical shock. So from the reverse shock that I mentioned to you before, the reverse shock is expected to produce these fast decay, and then the optical portion of the forward shock is the one that decays more slowly. So this is the reverse shock, and this is the forward shock. And a number of such quick optical flashes have been detected. And the question is, do the optical photons come more or less on do they have the same time behavior as the gamma rays? And the interesting thing is that sometimes they more or less seem to follow it. So the gamma rays are the full lines and the crosses are the optical observations. Sometimes they seem to behave more or less the same as the gamma rays. At other times they seem to behave differently. So it's thought that in those cases where the behavior is similar to the gamma rays, then it's probably the internal shock, it's the low energy asymptote of the synchrotron radiation of the internal shock that's producing it. Whereas when it does not correlate with the gamma rays, then it might be the reverse shock, which is a different shock than the internal shock, so it can have a different behavior. These are a list of the some of the optical flashes and how they correspond. Sometimes they don't correspond, sometimes they more or less do have a similar behavior with gamma rays. So a little compilation of the energy distribution. So during the burst itself, during the prompt emission, most of the total energy, about 65%, is in the MeV range. And in the X-rays, it's a smaller fraction. Optical is a very small fraction. And in the very high energies, in the GeV range, is maybe 10%. Then there is, so these might be the internal shock portion. This is the external portion, external shock portion. There, the X-rays and the low energy X-rays and high energy X-rays have more or less the same amount of energy. The optical maybe 3%. And there is usually also a radio component. Now you ask yourself, so what exactly are the progenitor objects? And I mentioned that for the long burst, it appears to be that it's the core collapse of a massive star. The core collapse of massive stars is thought to be the so-called core collapse supernova. So these thought to be something like a core collapse supernova, except that most core collapse supernova don't give rise to a gamma ray burst. So in this case, it's thought that the reason some core collapse supernova lead to a gamma ray burst is because these are the more massive stars, more massive than about 30 solar masses, where when the core collapses, it collapses to a black hole instead of collapsing to a neutron star. So most core collapse supernova are of less massive stars, 25 solar masses or less. There the core that collapses to a neutron star, and you get a normal supernova, no GRB. when the core collapses to a black hole, a very small fraction of the more massive stars, and if the core is rotating very fast, then you get the central black hole, and the central black hole can produce a jet which breaks out through the star and produces the gamma ray burst. It was confirmed that these long GRBs are accompanied by supernova by the direct observation of the spectrum of in the light curve. So the light curve, the optical light curve decays in time, but after 5 or 6 or 10 days, there is a second optical component that comes out, which is actually the light of the ejected envelope, which is the supernova envelope. And the spectrum of these ejected envelope corresponds to that of known type 1c supernova. So it's confirmed that these long bursts, they have a stellar progenitor, and it's associated to a supernova explosion. But it's a particular type of supernova explosion. It's a so-called type 1c supernova explosion. The spectrum is similar, but the ejector is ejected with somewhat larger velocity. Now, the velocity of the ejecta of the supernova is much, much slower than the jet. So the jet breaks out first. Its Lorentz factors of several hundreds. The envelope, the supernova, is ejected at subrelativistic velocity, or at most semi-relativistic velocity. So there are two different components. If the emission were isotropic, it would be a very large energy budget, something like a solar rest mass. And so that would mean that the whole energy of the whole rest mass of the star gets converted into gamma ray bursts. That's impossible because, you know, every process is inefficient. So what happens actually is that the emission is not isotropic. We know it's not isotropic because the light curve, which decays at a parabol, often shows a break and then a subsequent decay which is much faster. And that is thought to occur when so you have the relativistic jet, and it's becoming, as it slows down, the causality angle, which is 1 over the bulk Lorentz factor, eventually becomes comparable to the jet opening angle. And at that point, then you begin to see less radiation because your causal angle is larger than the actual jet. And so that's what causes these change in the behavior. And so from these break position, the time of the break, you can figure out what is the opening angle. And so the opening angles are of the order of 5 degrees or so. So without correction for the collimation, the inferred energies were distributed over a very wide range. But once you find out that there is a jet angle, then you correct for the collimation, and then you find that the energies is more or less distributed around 10 to the 51 ergs. So the energy requirement then is maybe 10 to the minus 3 solar rest masses for the radiation, and that's sufficient. Of course, you know that when you have a core collapse, most of the energy goes out in neutrinos and in gravitational waves, and those amount to almost like 70 or 80%. And what comes out in photons is only 1 part in 1,000. So that's a reasonable efficiency. All right. I'll mention briefly that there are two phenomenological relations. One of them is that the peak energy of the spectrum is correlated to the isotropic equivalent total energy to the 1/2. So this is the total energy of the burst if it were emitting isotropically. It's not, but you can always use a fiducial isotropic equivalent. And the other is that if you correct for the collimation, then the jet energy, the peak energy correlates with the jet energy to the 0.7. So this is an interesting correlation which has some cosmological uses, which I'll mention in the next lecture. So we know now that the long GRBs are core collapse of massive stars. They occur in star-forming galaxies. It remains the question, who are the progenitors of the short star GRBs? It was another satellite called Swift, launched in 2004, that made that type of advances. Again, this was a satellite which could slew, so it had a wide-angle gamma ray detector, and having obtained an approximate location of the burst, the spacecraft now was able to slew not in 8 hours, but in order of a minute. In a minute, it could repoint its X-ray detector, the XRT, and its ultraviolet optical detector, and so it could acquire a very good position very quickly. So up till now, it has discovered 815 afterglows, and of that, about 2/3 were detected in the X-ray telescope, and it has enabled obtaining redshifts for more than 250 objects, including 15 short GRBs. And so the typical redshift for the long GRBs is above 2. Previously it was thought to be for the 1, now it's known that the average redshift is larger. The short GRBs are typically at smaller distances, at lower redshifts. And so there are other interesting things that were discovered. So first of all, then, the short bursts were localized and the hosts were identified. And so it was found that they occur both in young and old galaxies, and they don't have a supernova remnant. So there is no supernova associated with them. And that is compatible with the suggestion that they're neutron-star mergers, or compact object mergers. The other thing that was a result of SWIFT was that, achieving so many observations with good locations allowed, pointing very large 8-meter, 10-meter glass telescopes very quickly, and obtaining redshifts. So a lot of high redshifts were obtained, redshifts 5, 6, 7, 8, and eventually even 9.2 over automatic redshift. And it started also enabling very prompt optical flashes, and some of them were even brighter. The other thing that we found is that the light curves, so typically with Beppo-Sachs, the afterglow light curves, I showed you the break, and this is the typical afterglow slope before the causal angle is reached, and this is the break point, and that's where you determine the jet size. But now SWIFT was able to measure things within the previous 8-hour period that had been unknown before. And so what it discovered is that the afterglows very often have a very steep decay portion and then a shallow decay portion, and then it rejoins the typical afterglow behavior. And sometimes there are flashes of X-rays in between. So the initial drop is thought to be due to the high latitude emission, the emission that is somewhat above the opening angle, and that will give you a delayed and softer radiation. And the shallow decay is thought to be due to the fact that you continue ejecting matter, so you have so-called refreshed shocks. I'm sorry, I don't have much time to go into the details for these. And the flares, the X-ray flares, those spikes I mentioned, are likely to be due to continued central engine activity. So it continues to eject shells that, make these internal shocks up to late times. So the location of the short burst then was identified. In some cases, the host was an elliptical galaxy. In other cases, it was a star-forming galaxy. But in both cases, it was compatible with an old stellar population, not a star-forming population, not a blue, massive star-type population. So this paradigm of the compact neutron-star merger is, even though it's not completely confirmed, but it's becoming more suggestive. And so numerical simulations then have been made about merger, let's say, of a black hole and the neutron star. And of course you can find out interesting things, that a Kerr black hole will have a different type of accretion history than a Schwarzschild black hole. and whether, so that has importance to determine what is the duration of the object. These are nice artistic simulations. There is not a scientific simulation. There is one of the scientific simulation. But NASA likes to do these public relations type of things, which are they look very good on the internet. But they give you the idea of what it is. So a big question that arose is, so one question is, so we know we have a jet, but what is the shape of the jet? Is it really a nice, straight-sided jet, a monolithic top-hat jet, or does it have a realistic structure, maybe a Gaussian structure? What kind of structure does it have? And some evidence for these came from the observation of a very interesting burst. There was this object which was detected by Swift, and it had a prompt optical detection. It so happened that the prompt optical detection was obtained with a telescope called Pie in the Sky. It was actually something that could have been seen with the naked eye. It was a fifth magnitude, so-called fifth magnitude star. Now you know that, maybe you don't know, but Hipparchus, Greek astronomer, before Christ, classified stars into first magnitude, second magnitude, third, fourth, fifth, and sixth magnitude. The sixth magnitude are the faintest you can see with your eye. Well, this was fifth magnitude, so in principle, if you had been looking, you would have seen, of course, it would have been one of the faintest stars, but with binoculars, you would have seen it very easily. And so the blue lines are the optical detection, the black ones are the X-rays. And so you can see that more or less they seem to, they sort of follow the gamma ray behavior. And so then you try to see whether you can model the afterglow light curve. So here's the X-ray light curve, and here's the optical UV light curve. And you see that there is something puzzling. It's not achromatic. The different wavelengths behave differently. So the light curve of the X-rays, they have a break downwards. The optical UV have a break upwards. And so that's not what you expect from a single monolithic jet, where the angular behavior is the same for everybody. In more detail, it turns out that it's possible to model it using a jet which has two components. One which is a broad component, which is a bit slower, smaller Lorentz factor, and the central core, which has a faster Lorentz factor. And both has a forward shock and a reverse shock, forward shock and reverse shock. And having different Lorentz factors, then you can actually reproduce the light curve. So you can reproduce there's the optical, the fit of the optical light curve, the reverse shock, Y jet, the forward shock, Y jet can reproduce optical light curve here. And then the X-rays are reproduced by the forward shock, the forward shock narrow jet, and the forward shock Y jet. So you need these composite structures. So the jet is obviously not monolithic, it has a structure. With better observations, one could get better details. Obviously, this is also a very simplified model, but at this level of data, you can model it with such a two-structured jet. Now, pushing on to the GeV range, the next interesting satellite to be launched was the Fermi satellite. Artist view of how it looks like. The instrument has two components. One is the Large Area Telescope, which is a high energy, basically it's sort of an incoming gamma ray breaks up into electron positrons, and then from the angle of the electron positrons you determine the energy, and then you use, of course, you track the direction, so you get the direction of the gamma rays. It also has a low energy monitor, so this has a 2-steradian field of view. We also use a low energy detector in the KV range, which is omnidirectional. So So it has these two detectors, the LAT and the GBM. And so it was launched in 2008. Good angular resolution, 10% in the 2080 to 300 GeV range. And it detects of the order of 300 bursts in the low energy detector per year, and maybe 10 or 12 per year in the high energy detector. So the detection statistics, have been published. It's roughly what is expected. And the interesting thing was that the first bursts that were detected with the LAT, at high energies, had the expected broken parallel, so-called band function spectrum, but the broken parallel extended into the 10 GeV range initially. So it started out being a soft spectrum, that the first time being A, next time being B, the spectrum has become very hard, and that extends into the GeV range. And then, still in the GeV range, the flux goes down, but it's still hard. So that was very nice. The puzzling thing was that one would have expected the GeV photons to come from an inverse quantum component, which would have been a second spectrum. Instead, it was just a single spectrum. So that was initially a puzzle. Another interesting thing was what I mentioned, that here are the light curves, and this is the low energy instrument, the GBM, and here is the LAT instrument, so energy increases this way. And you can see that the GeV photons, they come with a delay of several seconds relative to the MEV photons. And this is something that is observed in most of these bursts detected by the LAT, that the GeV photons lag significantly behind the MEV photons. And so there are various questions that arise in this connection. What causes these? Is it an astrophysical explanation, or are there other causes? You see these GeV lag, both in long bursts and in short bursts. So these are long bursts, these are short bursts. In both of them you see the lag. Eventually, as more bursts were observed, the second component was detected. So you see the initial band spectrum, and then the GeVs, they appear inside. In many of the bursts are connected not as an extension of the low energy spectrum, but as a separate component, a hard component. And this is what would have been expected from an inverse quantum component. So there were a number of theoretical issues. First of all, why in some cases you'll have only a single component spectrum extending to GeV, and which of the shocks produces it? Second, is it all leptonic? Is it electron synchrotron, or are there hadronic cascades involved in it? Because the high energy component could in principle be due to hadronic cascades. And then there was an interesting thing that you can actually obtain some limits on quantum gravity from these delays, but I'll talk about that tomorrow. In addition to such a possible quantum gravity effect, there has to be obviously, most of it must be an astrophysical explanation. And so what is the astrophysical explanation for this delay? And again, a number of models were proposed. I won't be able to review all of them. But for the delay, some simple examples in a leptonic interpretation are that you have initially, as the jet breaks out, there is a cocoon of gas which can produce an initial flash of photons. And then the internal shock can upscatter those photons. And that is the internal shock, while producing the MEV radiation, it also upscatters the soft photons into the GeV range. And because of the kinematics, you can get a time delay which is comparable to this few seconds delay. And you can produce a spectrum where you have, either a single high energy, broken parallel, or you can have, depending on the resolution, you can have also a second component. Another possibility is that the photospheric photons are being upscattered, and you get them, both the broken parallel band spectrum and the second component. So these are examples of leptonic models that can explain the delay and the spectrum. You can also explain them just on a simple internal shock and external shock model. More or less, you can explain the LAT high energy emission, the X-ray emission, and the optical UV emission with the afterglow. But the first few points of the GeV light curve have to be related to the prompt emission, to the internal shocks or whatever causes the prompt emission. So as I was mentioning, there is the second component, which in some cases is very clear. It's a 5 sigma detection. And so some possibilities are to associate it with hadronic cascade. So with Katsuaki Asano of ICRR, we had some models where you explain the MEV emission with a simple leptonic mechanism, and then the hadronic cascades that occur from accelerating protons, and the protons undergo P gamma interactions, so you get photomeson interactions and then hadronic cascades. Then you get the secondaries to produce synchrotron and inverse quantum radiation, which produces these second component. So you can make these fits of the spectrum also through such hadronic models. And interestingly, you could have predicted the bright optical flash of the naked eye burst with these hadronic secondary cascade electrons radiating at low energies. Okay, so let me mention now, so all nice things happen, lots of progress. Last year, the biggest excitement was these bursts here, 130427A, which had the largest apparent fluence. So most bursts have fluences which are 10 to the minus 4 per square centimeter or less. And these bursts had 1 order of magnitude higher fluence than most bursts. So it was the largest burst ever seen by 1 full order of magnitude in terms of flux. And the distance was determined. It was a fairly low distance, one of the closest bursts observed. So that, in a sense, explains why it had such a high flux, apparent flux. It's largely due to the fact that it was so nearby. Most bursts at a redshift of 1, 2, 3, or so, and these was at the redshift of 1/3. So clearly, since flux goes over the distance squared, it's not surprising that it's 1 order of magnitude higher than the maximum fluence observed before. It's very rare to find a burst, a long burst these near. It's an event that's 1 every 20 or 1 every 25 or 50 years, so it's very rare. And so because of the fact that it was so near, its total isotropic equivalent energy is more or less ordinary. It's what is expected. So the isotropic equivalent, of course, it's collimated, so the actual jet energy is more like 10 to the 51. So it's a normal burst. But being so nearby, it had a huge photon statistics, so a very good opportunity for detailed study. So when you look at it, it was a monster. And so there was a lot of press, that this was extremely exciting. And so there was a lot of hype. But some of the more sober people, some people said that it challenges the model, etc., need to revise understanding. But some other people said that it's an ordinary monster. And so the closest approximation is the latter. That it's just, by chance, it's an object which is very bright, and you have a very good opportunity to get more detail. and then you find that the models that we're using were somewhat simplified, so now you have an opportunity to refine